So this is the data sheet you got for question 9. So you'll have to refer back to this as we go. But part A on question 9 wants to know, it says the heat produced by the reaction can be calculated from the temperature change delta T using the expression below. Heat change equals the volume times the specific heat capacity times delta T. So basically MCAT, but we're going to use the volume because we're going to make a couple assumptions. And that's what they want to know here. What are those assumptions? Well, if we're going to use the volume of CuSO4, we're assuming that the density of CuSO4 is equal to the density of water. We're using the specific heat capacity of water, so we're also assuming the C value for CuSO4 is equal to the C value of water. A couple of other assumptions that you could mention is that we're assuming that all heat transfers, there's no heat loss. We're also assuming that the cup doesn't assume any heat, or the zinc. Okay, those would all be valid assumptions to make. Another one that I could mention that they commonly accept is that the limiting reactant fully reacts. And those are kind of the big ones that IB likes to hone in on. So then part B says, use the data presented by the data logging software to deduce the temperature delta T, which would have occurred if the reaction had taken place instantaneously with no heat loss. So what they want you to do is you plug into this equation minus 0.050 times, and this here is little t, which is your time, and the time is when we added the zinc to it. We added the zinc at 100 seconds. So little t or time there would be 100, and if we do that, we get a value of negative 73. And negative 73 then would have been the expected value. And so if I go ahead and subtract the 24.8 from that, actually this is positive 73, this is the negative 5 there. So positive 73 minus the 24.8 means my temperature change is 48.2 degrees Celsius according to my extrapolation. So state the assumption made in part B1. My assumption there is that I have heat loss, but that heat loss is constant or consistent. And that's why I can extrapolate back along my heat loss side of the graph. And then part 3 says calculate the heat in kilojoules produced during the reaction using the expression given. So now I'm going to go ahead and use my mass of my CuSO4, which was 50 grams. I'm going to use my C value for water, and I'm going to use the 48.2. When I get done, I need to divide this by 1,000 to have it in kilojoules, and that gives me 10.1 kilojoules. And if you wanted to express this in kilojoules per mole, that would be fine, since these are, the balanced equation is in moles of product. And then part C wants to know, says the color of the solution changed from blue to colorless. Deduce the amount in moles of zinc which reacted in the polystyrene cup. I don't know why you really needed to know the color change. I guess they're trying to give you evidence that it fully reacted. But if you look back to the balanced equation, they showed you that all the copper ion exchanges with the zinc atoms in a 1-to-1 ratio to give you zinc ion and leave copper atoms. So since I had 1 mole per liter of copper, that was my strength, and I had 50 centimeters cubed, which is the same as 0.050 liters. That means I had 0.050 moles of copper 2, and that means since it's occurring in a 1-to-1 ratio, I also have 0.050 moles of zinc that reacted. And then calculate the enthalpy change in kilojoules per mole. And actually, I misspoke back when I said you could express this as kilojoules per mole, because the 10.1 was for 0.050 moles. So now I should divide that, and I get negative 201 kilojoules per mole for this reaction. Okay, number 10 I thought was a little kinder and gentler than 8 and 9 were, and I apologize I didn't order that test very well. 8 and 9 should have been toward the end. But you've got your data. This is very similar to the one you just looked at, but in this case it's sucrose. And it says the sample was 0.435 grams. The heat capacity of the system, now this is capital C. It's not the specific heat, it's the heat capacity. So you notice the unit is 10.114 kilojoules per Kelvin degree. That would be exactly the same in Celsius degrees, because a Kelvin degree and a Celsius degree are exactly the same amount of energy. They're just 273 degrees apart on the charts. So it says calculate delta T for the water. This is really as easy as it looks. You start at 2303, you go up to 23.7, so you just subtract these two, 23.7 minus 2303, and your temperature change is 0.67 degrees Celsius. Determine the amount in moles of sucrose. So now you take your 0.435 grams of sucrose, 0.4385 grams, and you have to divide by the molar mass of sucrose, which I calculate to be, it's like 342, it's a big molecule, 342.34 grams. So I came up with 0.00128 moles of sucrose. So calculate the enthalpy change for the combustion of 1 mole of sucrose. What they expect you to do here was take the 10.114 kilojoules per Celsius degree times the degrees that you changed the temperature, 0.67 degrees. That will give me kilojoules. And then I can go ahead and divide by my molar amount, which is 0.00128. So I come up with a delta H of 5294 kilojoules per mole. And then part 2 says, using the data booklet, calculate the experimental error. Well, if you check in the data booklet gives a value of 5,640, and when I subtract my calculated value of 5294, my experimental error is 346. So I put the error over the expected value times 100%, and I get an experimental error of 6.1%. And then part D, it wasn't very difficult if you hadn't given up completely by then. It says a hypothesis is suggested that TNT is a powerful explosive because it has a large enthalpy of combustion, a high reaction rate, and a large volume of gas generated upon combustion. Use your answer in part C1 and the following data to evaluate this hypothesis. And it's worth 3 marks, so basically you have to address each question. And what they're showing you here is they're showing you the equation for sucrose and TNT along with the rate, the reaction rate, and the enthalpy of combustion. So a large enthalpy of combustion, well, we just calculated sucrose's to be over 5,000. So negative 5294 is what we calculated. So certainly burning sugar, if you ever burnt a marshmallow in a fire, that is not an explosive reaction, and that releases far more energy per mole. So a large enthalpy of combustion, no, because sucrose has the greater delta H. A high reaction rate, okay, that could be legit. TNT does have a higher reaction rate than sucrose does. How about a large volume of gas? Well, if I look at it, I've got 12 moles and 11 moles. I've got 23 moles for sugar being produced. And over on the TNT side, I have 7 plus 5 plus 3. I have 15 moles. So no, sucrose is producing more moles of gas. So apparently the only one of these 3 claims that has some validity is the high reaction rate.